In this video, we are going to look at a test which is sometimes called the comparison test. I like to be a little bit more specific than that, so I'm going to call this the ordinary comparison test. I'm going to state it, then we'll do several examples, and then we'll work through the proof of the ordinary comparison test. Okay, here's the statement of the ordinary comparison test. We're going to make a comparison. So what we have are two sequences of terms, an and bn. Both are non-negative, and an is less than or equal to bn for all terms in each sequence. In other words, a1 is less than or equal to b1, a2 is less than or equal to b2. That's how you can read that inequality. So we have this relationship between all corresponding pairs of terms from each sequence. The ordinary comparison test consists of two statements. The second statement is going to be a restatement of the first one. I'll show you what that means, but both of them give us results. So both of them are tests that we will apply. The first statement says if Bn forms a series which converges. So if I take those terms and add them up into a series Bn, where it doesn't matter where I start indexing, but let me write n equals 1, could be n equals 0, as you know, it could be any lower index, but this is an infinite series. If this series converges, then the series that we would get from the terms a sub n also converges. What this says is if I am able to add up the larger numbers and have them add up to something finite, so this sum exists and equals a finite number, then since these terms are smaller, if anything smaller, they are also going to add up to something finite. So this is not going to grow to infinity if all of the terms are smaller than something which doesn't go to infinity. Okay, so if the larger one converges, the smaller one converges. This is what's called an if-then statement in mathematics. So if P, then Q. So here P is the idea that the series of larger terms converges. Q is the idea that the series of smaller terms converges. So if the series with Bn converges, then the series with An converges. An if-then statement in mathematics is logically equivalent to what's called its contrapositive. The contrapositive of an if-then statement is if not Q, then not P. Right, not. All if-then statements have this relationship that this statement is true when this statement is true, and this statement is true when this statement is true. They're either both true or they're both false. So if this statement is true, so is its contrapositive. What is the contrapositive of this statement? It's if not Q, then not P. So I'll do this out loud and then I'll write it in a better form. That would be if it's not the case that AN converges, then it's not the case that BN converges. But not converging is called diverging. So the better way to phrase the contrapositive of this first statement is if the series with AN diverges, then the series with BN diverges. So both of these are tests in their own rights, meaning that it's worth having both of them as statements on hand. So this is not Q, it's not P. So I would really remember both of these statements as they're written. Let's talk through what the second one says. Again, we have this ordering where the AN terms are less than or equal to the BN terms, and everything here is positive. So as we're adding, the sum just grows larger and larger. That means that if AN forms a series which diverges, then as I add up these terms, they're adding up to infinity. The BN terms are, if anything, larger. So if this is adding up to something that grows to infinity, this also has to grow to infinity because if anything, it's going to be bigger. All of the individual terms are bigger. So for me, the ordinary comparison test says smaller than converging is converging, larger than diverging is diverging. Notice that there's nothing here about what happens if you are bigger than something converging, because that's kind of useless. If something is converging and you're, much larger, the behavior of the convergent series says nothing about the behavior of you as the larger series. Similarly, there's no result here that gives us any information about being smaller than a divergent series, right? So if you have a series that's diverging and you know a different series is smaller, you don't know anything because this might be going to infinity and this one might be converging. So it's really telling us that smaller than converging is converging, larger than diverging is diverging. Okay, let's start with the series of terms that look like 1 over n squared plus 1. Now, what you want to do when you look at something like this is say, does that remind me of a famous or recognizable series? For example, a geometric series or a P series. That's where my mind tries to go first. And 1 over n squared plus 1 looks a lot like the convergent P series 1 over n squared. Here's the comparison that we can make. We can say that 1 over n squared plus 1, for any index n, this number is less than or equal to 1 over n squared. Keep this in mind. When we're looking at non-negative terms, if you make the denominator smaller, you make the fraction bigger. So by removing the plus 1, I made the denominator smaller, therefore I made the fraction bigger. So cutting out that plus 1, you go up in size. So we're now saying that the terms 1 over n squared plus 1 are smaller than terms which form a convergent P series. So therefore, this series converges. So what I'm going to say is this is smaller than that or less than or equal to that. And the series from n equals 1 to infinity, 1 over n squared, is a convergent P series. So the series that we have converges by comparison. Actually, I want to be a little bit more precise than this. This is the whole reason I want to bring in this language of ordinary comparison, because we have other types of comparison. So let's be precise. I'm going to say converges by the ordinary comparison test. Okay, so this would be a full explanation of why this series we can figure out converges using the ordinary comparison test. So what we did was we compared it to a known P series, stated that that converges. So you want to explain why you know that converges, and therefore the series that we started with converges by the ordinary comparison test. I'm going to step away for a second in case you're copying this down, and then I'm going to erase this to give us enough room to look at the second example. For the second example, we have 1 plus the square of cosine of n divided by n. Again, you want to look at that and think, does that remind me of something I already have studied? And if I just focus on the first term in the numerator and the denominator, it looks like a 1 over n. So then what kind of comparison could we make with this expression and the harmonic series 1 over n? Well, the thing is cosine squared is always greater than or equal to 0. So if I take 1 plus cosine of n squared, divide that by n, this cosine term in the numerator, since we're squaring it, This is always between 0 and 1. So if I remove it from the numerator, if anything, we get smaller. So this is greater than or equal to 1 over n. And this forms the series which we know to diverge. This is the harmonic series, or the terms in the harmonic series. So this is the comparison. Since I'm going to leave off indices. The series 1 over n is the divergent harmonic series. Then the series that we're trying to analyze diverges by the ordinary comparison test. So I'll say this series diverges by the OCT. Okay, so these are two examples where all we had to do was kind of knock off terms. As you do that, you want to think about the direction that you take your inequality. So again, knocking off a term to make the denominator smaller makes a fraction bigger. Knocking off a term in the numerator makes a fraction smaller. So just be careful if you're making a comparison by kind of removing what feels like extraneous information that you can get rid of in order to arrive at a more classic looking series expression. Just be sure that you're preserving the direction of the inequality that you need. Here, we were smaller than something that we knew to converge. So this was a valid setup for the ordinary comparison test. Here, we are larger than something we know to diverge. So again, this is a valid comparison to make for the ordinary comparison test. I don't want to get too off topic with hypothetical situations, but if we had been smaller than something divergent, we wouldn't have been able to proceed because being smaller than a divergent series doesn't tell you anything. Similarly, if we had been larger than something convergent, again, there's no conclusion that we could get from that because being larger than something that converges, you don't know, how to, you can't extend that convergence to the larger series. So look at your series, try to figure out if it reminds you of a series that you understand, and then see if you can arrange a suitable inequality, which is true, and the correct direction to give you an actual conclusion. Let's use the ordinary comparison test to figure out if the series that looks like 1 over n factorial from n equals 1 to infinity converges or diverges. So n factorial is an expression that means take n and multiply it by every lower integer number until you get down to 1. Okay, so let me write it down. N factorial is going to be the product of n times n minus 1 times n minus 2. And you keep going until you get down to, say, times 3 times 2 times 1. So 3 factorial is 3 times 2 times 1. 4 factorial is 4 times 3 times 2 times 1, etc. So let's assume that n is at least 3. I mean, we're looking at n going from 1 to infinity. So if n is at least 3, what I'm going to do is take every term larger than 2 and replace them with 2 in this product. So n factorial is greater than or equal to taking this number and replacing it with 2. So this number decreased down to 2. Take this number, replace it with 2. Take this number, replace it with 2. And keep doing that until you get to the 3. Leave the last 2 alone. Let's see, how many 2's do I have here? So I've got 1, 2 sitting under 2, 3. So if I got a 1, 2, 3, 4, I would be under 2, 3, 4, all the way up to n. All that to say that this number of 2's is 1 less than this number. So the number of 2's I have here is 1 less than this number. So this number is equal to 2 to the n minus 1 times 1. Okay, so n factorial for n, let's say, greater than or equal to 3. I think it also works when n equals 1 and 2, but we're focusing on n greater than or equal to 3 here so that we can do this lowering process. N factorial is greater than or equal to 2 to the n minus 1. So let's take the reciprocal. 1 over n factorial is going to be less than or equal to 1 over 2 to the n minus 1, which is fine as it is, but if you wanted to, you could write that as, say, 2 times 1 over 2 to the n. This is a series that we recognize. This is a convergent geometric series with r equal to 1/2. So I'm going to be less wordy now in my explanation. I'm just going to write convergent geoseries. Which means that this converges by the OCT. So since the terms 1 over n factorial were smaller than terms that we know form a convergent series, in particular a convergent geometric series, we are smaller than something converging, so we're converging by the ordinary comparison test. What I'm going to do here is take n factorial and n to the n, recognize each of those as a product. So both of these expressions are concise ways of writing products. So let me expand each of them. In particular, n factorial is the product of consecutive integers. So I can write this as n times n minus 1 times n minus 2, all the way down to 3 times 2 times 1. So there are n terms in that expression. Let's divide this by n to the n. This means multiply n times itself n times. So that's n times itself n times. So under each of these terms, I'm going to write a copy of n. So both the numerator and denominator are products which naturally can be expanded into n terms. Okay, I want you to look at these, take a minute and see what kind of replacement or comparison you might want to make. Notice that because they each have n terms, we can think of like this first pairing, this second pairing, this third pairing. We have kind of a natural pairing between terms in our numerator and terms in our denominator. So experiment with this, and then I will come back and show you what I would do in order to set up this expression for an ordinary comparison test. Okay, so here's where my mind would go looking at this the first time. These terms are very similar, but when I look at the end of this fraction, if you will, I've got 2 over n, 1 over n. That kind of reminds me of like a p-series expression. If I was just looking at these last two terms, it would be 2 over n squared. So can I somehow get rid of the rest of the terms and just have something that captures this ending behavior for the numerator and denominator? So, well, how could I get rid of them? I could get rid of them if they had the same numbers and I could cancel out. So what I would do here is take each term in the numerator and raise it to n. It's almost like the reverse of what we did in the previous example. So I'm going to take these terms and increase them up in size. So we will make our fraction larger by making terms in the numerator larger. So in particular, n stays as n, but then this n minus 1 term is going to become n. So I'm going up in size. N minus 2, let's replace that with n, and keep going until we get to replacing 3 with n, and then leave 2 and 1 as they are. This is my new numerator. Divide it by the original denominator, n times n times n, all the way down to n times n times n. Then this is a much easier fraction to work with because everything to the left of the 2 and everything corresponding down here in the denominator, these are all going to cancel. So that cancels with that, this cancels with that, cancel, 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 cancel. And we are left with an expression that tells us that our original series terms are less than or equal to 2 over n squared. The 2 is just a constant multiple. This is twice 1 over n squared, which is a convergent p-series. So I'll write convergent p-series. So that means that our original series converges by the ordinary comparison test. Okay, so this was another kind of challenging exercise where you see this factorial expansion and you want to expand it out. I think it's helpful to actually see the terms, and then you might not get to this the first time, but you start trying to think, is there any way for me to alter this and maybe go up in size so I can make a comparison with a convergent series? Or if it was relevant, maybe go down in size to compare to a divergent series that's smaller than or equal to the terms we have. Here, this converges, so the correct direction to go was to increase the size of our expression so that we would be smaller than a series that we know to converge. Now let's look at this example where the series terms look like n plus 3 to the n over 5 to the n. Let me first set up a comparison which is not a good one, and then we'll switch to a good comparison. So your first attempt might be to say, hey, let's knock off that n from the numerator because 3 to the n and 5 to the n look like geometric series. So you could say n plus 3 to the n divided by 5 to the n. If I got rid of the n from the numerator, then I'm losing size. We go down if we get rid of that n. So n plus 3 to the n over 5 to the n is greater than or equal to 3 to the n over 5 to the n, which is 3/5 to the n. And this is a convergent geometric series. However, this is a useless comparison to make because being larger than something that converges doesn't tell you anything. So this series might converge, but if this one is much, much larger, it might be growing to infinity. So being bigger than convergent is not a valid comparison to make. So we're going to have to try something else. So what we should try instead, since this didn't work, let's try to make a better comparison. It might still be with the geometric series, but we just have to set up the inequality correctly. So try instead. What if I took that n and instead of getting rid of it, I replaced it with something that could kind of fit in with this geometric series pattern? So I've got 3 to the n, 5 to the n. Let's replace n with maybe another copy of 3 to the n. So how about n plus 3 to the n over 5 to the n? Take n and replace it with the term that we already have in the numerator so that we just have twice some expression in the numerator. This is less than or equal to 3 to the n plus 3 to the n over 5 to the n. So I replaced n with 3 to the n. N is just a straight line function, right? So that's just going to go 1, 2, 3, 4, 5. 3 to the n is exponential. So this is larger than that. You can try out a few terms if you don't see it right away, but this exponential growth is going to be larger than just plain old n. But what is this? This is two times this geometric series, and that still converges. So by making the correct replacement for n, going up in size, we are able to show that our original series is less than or equal to something that we know to converge, and therefore this series converges by the ordinary comparison test. Now I would like to take you through the proof of the ordinary convergence theorem. There were two statements, but because they were logically equivalent, the second one was the contrapositive of the first one, we only need to prove the first one. That was the idea that being smaller than a convergent series meant that you also converged. So I've started the proof here. Suppose that the series of terms b sub n adds up to the finite number capital B. So this is a convergent series, and I should probably add the rest of the information from the ordinary comparison test here. And 0 is less than or equal to a sub n is less than or equal to bn for all n. Okay, so that's the situation we're looking at. I would like to show that the series of terms made out of, the series made out of the a sub n terms also adds up to something finite. It converges. What we are going to do is go all the way back to the definition of when a series converges. We say a series converges if its sequence of partial sums converges. So let's start writing down some partial sums for the series a sub n. Notice the sequence of partial sums for the new series from n equals 1 to infinity of a sub n satisfies that the first one, s sub 1, is the first term in the series, that's a sub 1, but a sub 1 is less than or equal to b sub 1. And since everything here is positive or non-negative, if I take b sub 1 and add to it b sub 2, 3, 4, 5, we only go up in size. So the first term in this series is less than or equal to the total series. Because this series has b1 and more. But this series is a number. It adds up to the number b. Okay, what about the second partial sum? S sub 2 is a1 plus a2. But a1 is less than or equal to b1, and a2 is less than or equal to b2. B1, I'm switching letters to b. Okay, so b1 plus b2. And just like the line above, I have the first two terms from the series b. If I add to it b3, b4, b5, etc., if anything, we only get larger. So this is less than or equal to the number b. And in general, the kth partial sum made up of adding the first k terms from the an series, this is less than or equal to the first k terms from the bn series, which again is less than or equal to b. There are two properties of the sequence of partial sums that I would like to make right now. One is the observation I'm really going for here, which is that each partial sum is bounded above by the same number b. The second observation to make, it's a little bit subtle, but if you look here and keep in mind that all of the terms are non-negative, the sequence of partial sums is monotone increasing. So let me do that over here. Notice s sub k plus 1 is greater than or equal to s sub k for all k. And all partial sums are bounded above by b. So we have a monotone increasing and bounded sequence. By the monotone convergence theorem, we know it converges. I'm like really struggling to spell correctly. So monotone convergence theorem, we know that the sequence of partial sums for a sub n converges. But if the sequence of partial sums for an infinite series converges, that is literally the definition that the series converges. So we can wrap up. I don't really know where to write it. Let me write it down here. Thus, the series, the infinite series of terms a sub n, also converges. It would converge to whatever the limit of the sequence of partial sums is. We know that limit exists by the monotone convergence theorem. I can't tell you what it is. I guess the best thing I could say at this point is it's less than or equal to the number b. All right, so that concludes the proof of the ordinary comparison test. In the next video, we will look at another comparison test called the limit comparison test.